In 1901, sponge divers off the Greek island of Antikythera found a Roman shipwreck on the seafloor. Among statues and amphorae, they recovered a small, corroded lump of bronze that seemed insignificant. At first, the object was catalogued as debris, possibly a broken tool or decorative fragment from the ship. Nothing about its shape suggested importance, and it was stored away while larger artifacts drew all attention. But as the bronze slowly dried and cracked, something unexpected appeared inside the corrosion. Perfectly shaped gear teeth, locked together, arranged with deliberate mechanical intent. This was not decoration, and it was not accidental damage. These gears were cut, aligned, and designed to move, suggesting a level of mechanical planning no one believed existed in the ancient world. The problem was not understanding what the object was made of. The problem was understanding why such a machine existed at all, in a time with no motors, no electricity, and no industrial tooling. Because this device was not measuring weight or motion. It was calculating time, predicting eclipses, and modeling the sky itself, 2,000 years before such machines were supposed to exist. To understand why the Antikythera mechanism was so unexpected, it helps to look at the world it came from. In the 1st century BCE, complex machines were rare, fragile, and almost always simple in function. Most mechanical devices of the era were designed to move water, lift weight, or track basic time. None were meant to model abstract systems, let alone predict events in the sky. Yet the Antikythera mechanism was not built to push, pull, or lift anything at all. Its purpose was calculation, turning astronomical cycles into mechanical motion. This meant the machine was designed around ratios, not force. Every movement inside the Antikythera mechanism represented a relationship between time, motion, and celestial patterns. In an age without standardized parts or precision tooling, this level of mechanical abstraction was unprecedented. The Antikythera mechanism assumed a user who trusted systems, not observation alone. This is what made the device unsettling to modern historians. It did not fit the technological ladder we believed humanity had climbed, because it stood several steps ahead of its time. The Antikythera mechanism was built almost entirely from bronze, an alloy of copper and tin commonly used for tools and weapons. What made this choice unusual was not the material itself, but how precisely it was shaped. Each gear of the Antikythera mechanism was individually cut, not cast, with teeth shaped to transfer motion smoothly. This required controlled spacing and consistent angles, achieved without modern measuring tools. The irregularities visible in the gears are not flaws, but evidence of manual craftsmanship. They show that precision was achieved through skill and repetition, not machinery. Despite being handmade, the gears maintained accurate ratios over long sequences of motion. A small error in tooth count would have broken the astronomical cycles the Antikythera mechanism was designed to represent. The components were mounted inside a wooden case, likely made from local hardwood. This enclosure protected the gears and kept their alignment stable during operation. Nothing about the construction suggests experimentation or improvisation. The Antikythera mechanism appears fully planned, as if its builder already understood the entire system before the first gear was cut. More than 30 bronze gears have been identified inside the Antikythera mechanism, arranged in tightly connected sequences. Their placement was not decorative, but functional, forming a continuous mechanical logic. Each gear carried a specific number of teeth, chosen with mathematical intent. In the Antikythera mechanism, these numbers mattered more than the size of the gears themselves. When one gear turned, it did not simply pass motion forward. It translated one cycle of time into another, preserving ratios that mirrored astronomical periods. This is why the device can be described as computational. The Antikythera mechanism did not store numbers, it embodied them through motion. Turning a single hand crank activated the entire system. With one input, multiple outputs emerged, each synchronized but independent. This is not how simple machines behave. It is how models behave, reducing complex reality into a controlled mechanical system. The Antikythera mechanism did not calculate by approximation. Its accuracy depended entirely on whether its internal relationships were correct. In this way, thought itself became mechanical. The Antikythera mechanism transformed human understanding of the sky into a physical machine that could be turned by hand. The front face of the Antikythera mechanism carried a circular dial marked with the zodiac and the solar calendar. This surface translated celestial motion into a readable mechanical display. As the mechanism was turned, the sun pointer completed one full rotation per year. This movement reflected the apparent annual path of the sun across the sky. The moon was modeled differently because it does not move at a constant speed. Its pointer advanced unevenly, reflecting the moon's changing velocity along its orbit. To achieve this, the Antikythera mechanism used an offset gear system that mechanically reproduced irregular motion. This principle would not reappear in known technology for many centuries. The result was a mechanical approximation of the moon's elliptical orbit. Without equations or calculations, the machine captured a complex astronomical truth through motion alone. This level of astronomical modeling was not intended for casual observation. It assumed users who trusted the mechanism to represent the sky more reliably than the eye. While the front dial showed the rhythm of the year, the most advanced functions of the Antikythera mechanism were hidden on the back. Here, time was compressed into spiraling scales designed for long-term prediction. One of these back dials represented the Metonic cycle, a 19-year period that aligns lunar months with solar years. This allowed the Antikythera mechanism to keep its calendar synchronized. Another spiral dial tracked the Saros cycle, which governs the repetition of eclipses. This cycle made it possible to predict when the sun, moon, and Earth would align. These predictions were not observational guesses. The Antikythera mechanism encoded astronomical knowledge directly into its mechanical structure. By turning the mechanism forward in time, future eclipses appeared automatically on the dial. The machine revealed events years in advance without requiring the sky to be watched. Inscriptions near the eclipse indicators specified whether an event would be lunar or solar. Some even included details about visibility and timing. This level of prediction required more than astronomy. It required confidence that the universe followed repeatable patterns that could be trusted mechanically. For its time, this was an extraordinary assumption. The Antikythera mechanism treated the cosmos as a system that could be reduced, modeled, and turned by hand. The Antikythera mechanism did not rely on a single universal calendar. Instead, its markings reflected a specific Greek calendar system used in daily civic and religious life. This choice meant the device was designed to be practical, not theoretical. The Antikythera mechanism was built to function within the timekeeping systems its users already trusted. Different inscriptions suggest that the calendar could be adapted for regional use. This implies a level of customization rarely associated with ancient mechanical devices. By linking astronomical cycles to a local calendar, the Antikythera mechanism transformed time into a manipulable system. Turning the device meant moving through months and years mechanically. This approach treated time as something that could be engineered. Days, months, and years were no longer abstract ideas, but physical states of a machine. In doing so, the Antikythera mechanism blurred the line between observation and control. Time was no longer only experienced, it was operated. No workshop capable of mass-producing a device like the Antikythera mechanism has ever been found. There were no factories, no standardized parts, and no industrial infrastructure to support its creation. Yet the precision inside the Antikythera mechanism makes accidental discovery impossible. Its design required deep understanding, careful planning, and years of accumulated knowledge. This suggests the work of a small circle of highly skilled individuals, rather than a broad technological culture. The Antikythera mechanism was likely built by specialists operating at the edge of what their world allowed. In that sense, the device was not the beginning of a technological era. It was the peak of a narrow tradition that left almost no trace beyond the machine itself. The Antikythera mechanism did not disappear because it failed. It disappeared because the conditions that supported it quietly collapsed. Without institutions to preserve specialized knowledge, complex systems are fragile. When skilled individuals vanish, their techniques often vanish with them. Bronze was valuable, and machines were often melted down for reuse. The survival of the Antikythera mechanism was an accident of shipwreck and burial. What remains today is not just a device, but a message. It shows that advanced thinking does not always move forward in a straight line. The Antikythera mechanism stands as proof that human understanding once reached far ahead of its time, then quietly vanished, leaving gears behind as its only record.